Hello, my name is Bernardita Ried Guachalla. I'm a PhD candidate at Stanford University, and thank you so much, Cosmology from Home, for having me. I am super excited to talk about a challenge that is currently spanning different areas of astrophysics and cosmology, and in particular, I wanted to present this talk titled Backlighting Extended Gas Halos Around Luminous Red Galaxies. And we measure this through the kinematic Sunyaev-Zel'dovich effect, in particular using CMB or cosmic microwave background data and large-scale structure. This allows us to overcome one of the biggest challenges right now we're facing in galaxy surveys, which is the missing variance problem. So if you go to any galaxy survey, what you will see will be mainly the galaxy starlight, which corresponds to approximately 10% of the baryonic content of the universe. So in here I'm illustrating that, in which you can see this is a illustrative simulation in which I'm showing the stellar component, the dark matter, and then the gas density. The gas density we find to be much more extended than the galaxies themselves. And localizing this variance is not easy because they do not necessarily follow dark matter because they have electromagnetic interactions, and that is why it's tricky to localize them. And if we can actually observe them directly, we could learn about, for example, astrophysics, because in the galaxy formation and evolution scenario, we have feedback processes such as AGN or supernovae that can redistribute gas and also impact the stellar formation. And also another aspect that could be impacted by the distribution of this variance is galaxy lensing, because if we have large components of matter redistributed in the outer skirts, this could also impact the lensing you can have. Therefore, a solution we can use is to use the CMB, or the cosmic microwave background, as a backlight. So CMB photons travel through the universe and go through the large-scale structure and then reach us. However, these do not necessarily do it in a straight line, as it is illustrated here. They can get lensed or scattered due to the electrons or free electrons of these galaxies. If we can use that information to trace the gas, we can get a lot of physics from the distribution of baryons. So in particular, if we have good resolution, we can measure the so-called kinematic Sunyaev-Zel'dovich effect through this method. So the kinematic Sunyaev-Zel'dovich effect is mainly the Doppler shift of CMB photons due to large-scale structure that has peculiar velocities with respect to the expansion of the universe. In other words, we use the fact that galaxies move because they feel the gravitational attraction of each other. So in here I'm showing two clusters that feel the gravitational attraction of each other. One is moving away from us or away along the line of sight, and the other one is moving towards us, also along the line of sight. In this figure, we see that the CMB photons that interact with the gas of these baryons get Doppler shifted depending on the velocity along a line of sight. Therefore, this effect, we can summarize it as follows. The change of frequency of the CMB photons are proportional to the number density of electrons, because if I have more electrons, this effect will be higher, and also proportional to the velocity along the line of sight. Because if this velocity is higher, this Doppler shift will be also higher and will change sign depending on this velocity too. If we are able to isolate the number density of electrons, as I said, we understand a lot about astrophysics, about the missing variance problem. But if we can also isolate, for example, the velocity of these galaxies through the kSZ, we can learn a lot about the growth of structure. And in particular, I'm more interested in the first one because, as I said, I want to find where the missing variants are. And this is, for example, a measurement that you can do. I'm going to explain more the details, but mainly what I want to show is that we have already done this. We have already studied the gas through the kSZ and found that it's way, for example, more extended than galaxies themselves. And in order to get a signal like the one I'm showing you in the bottom left, you need to estimate the galaxy's velocities. And for that, we use this so-called velocity reconstruction method. We can study the velocity field of galaxies just by their distribution. In other words, you can use the linear version of the continuity equation as shown in here, in which you have that the gradient of the velocity is proportional to the number density of galaxies. In other words, here in the bottom part, we have that each dot represents a galaxy in the simulation. And if you use the equation above, you can get that the displacement you expect from galaxies moves towards these overdensities, and therefore you expect that overdensities attract galaxies nearby. In particular, you can include redshift space distortions, and this is actually an equation that is not new, it's used in BAO analysis, and in that world is called BAO reconstruction. So we have different questions about these methods, which include what can we improve for previous implementations on the context of the kSZ, and which variables do impact the reconstruction. And for that, we had two teams working, one here at Stanford, in which we worked to understand localized impacts of, for example, redshift space distortions, photo Z noise, and other things, while we had another team in Berkeley working on realistic light cone mocks that told us how this impact in real kind of observations. We use the N-body from Abacus Summit, and in particular in here, I'm showing a 2 gigaparsec box in which the GIF oscillates between the true and reconstructed velocities. Red represent galaxies moving away from us, blue towards us, and as you can see, the degradation is not as bad just visually. The key results of this work are, we found that the reconstruction velocity works really well on halos rather than galaxies, which is really convenient for kSZ, because we expect the gas follows the dark matter halo distribution rather than the galaxies themselves. So in here I'm showing the 2D histogram of what would be the correlation between the true velocities and the reconstructed velocities in a simulation. And as you can see, these tend to follow a line that corresponds to a perfect correlation. This is in log space. However, when we reconstruct galaxy velocities, there's some anti-correlation due to redshift space distortions, inherent to, for example, satellite galaxies. However, when we study the halos itself, not the galaxies, we find that this anti-correlation decreases substantially, and our correlation coefficient, which is a quantity we use to evaluate how good this method is much higher. And the other reason why we use the correlation coefficient is because this parameter is actually proportional to the signal to noise you can get when you measure the kSZ. Another important result is that we found that it's really robust on numbered densities. So in here, I'm showing the same box, but now changing the number density of galaxies. And what we find is that it's really robust. And that allows us to do survey planning and understand that we maybe do not need a super high number density to do an accurate velocity estimate due to the fact that we're mainly reconstructing large scale velocities. And finally, one of the most important results is the fact that we observe that photo Z's are not a big problem for our measurement because sample size compensates. So here at the top, I'm showing the same box, but now I'm increasing the photo Z noise such that I can even reach a LSST-like expected noise. So on the bottom right, we see that as I increase the photo Z uncertainty, this correlation coefficient goes down by a factor of 2 more or less. And as I said, this is proportional to the signal to noise of the kSZ. Therefore, we're finding that having photo Z's decreases my signal to noise by 2. However, we can make this up by the fact that photometric surveys have way more galaxies than spectroscopic ones. And this is one of the key results of this paper, which illustrated us that we can actually use photo Z's to measure kSZ, something that people were not necessarily expecting with this method. Therefore, given that we learned this, immediately went to measure this with data. So I'm also presenting the results here on the kSZ when you use DESI data. So DESI is a dark energy spectroscopic instrument, and also the Atacama Cosmology Telescope, which is a telescope that just released its latest data set that is from the cosmic microwave background. We did a spectroscopic and photometric measurement because DESI also had a photometric counterpart, and my team is shown here, the same as the one we worked on the velocity reconstruction, which is Boriana Hadiskia, Simone Ferraro, both of them at Berkeley, and Emmanuel Sean here at Stanford. Let me show you how the velocity reconstruction field looks when you go from BOSS to DESI year 1. The way we detected the kSZ is the following. We went to our CMB map and localized where these galaxies are in the 2D field. And if you naively go and stack over them, you will not get any kSZ signal. Because our kSZ signal is positive and negative depending on the velocity of the galaxy you're considering. And as we expect that more or less half of the galaxies will be moving away from us and the other half moving towards us on top of the expansion, they will cancel out. In order to measure it, we do weight by the velocities, and that will enable us to have a signal. And that is in particular the blob I was showing at the beginning, in which if we stack the CMB map on the galaxy's position and we weight by these velocities estimated through the linear continuity equation, we get this. In order to exclude the CMB primary anisotropies from our measurement, we use this so-called compensated aperture photometry, which mainly selects a circle and subtract an outer ring of the same area, such that we can extract larger contributions from the outer rings. This allows us to reconstruct a profile that looks like a cumulative profile. And this is how our measurement looks. In here, the brown data points correspond to the signal. And as I said, we go to different apertures, measure this compensated aperture photometry, and this is the signal we get. In smaller scales, we have a lot of information, and larger scales are usually correlated due to CMB primary noise. Importantly, when we compare our results to simulations, and in particular with Illustris and Illustris CNG, we find that when we compare to dark matter, we're definitely finding gas that is way more extended than the classic NFW profile of dark matter. So in here, the black dotted lines correspond to dark matter, and for the same aperture, we find that we are still enclosing a lot of gas. There's another result that is interesting, which hints for a preference of models of galaxy formation that has stronger feedback. So in here, I'm showing the Illustris CNG curve at the same effective redshift compared to Illustris at different redshifts. And as we can see, Illustris at redshift 0.5 really matches well our observations, while Illustris CNG diverges more. This is hinting that probably the gas that we're finding is way more extended than we thought. However, there are two caveats in this plot, which is first one, we allowed the amplitude to free such that we can compare the shape of the profiles. And there might be other systematic effects that could be entering into our modeling that we're currently working on and exploring through simulations in order to confirm the conclusions I'm showing in here. Another main result of this work was that we explored the kSZ dependence with various galaxy parameters. So here on the right, I'm showing the different amplitudes of the kSZ profiles for different redshift bins. And as you can see, there's no clear or significant trend with redshift. However, we find a clear trend with stellar mass and absolute magnitude and different bands when we bin our data. This is really important and hints us a lot about galaxy formation models that impact different scales, masses, and luminosities. Another key result is that we did the first measurement with galaxies that were not necessarily luminous red galaxies, but BGS or bright galaxy sample or emission line galaxies as shown in here. However, the constraining power is not the same, but this still helps us to understand the physics that govern different redshift and types of galaxies across the universe. Another main result is the consistency we found with profiles when we compare spectroscopic and photometric luminous red galaxies. In here, I'm showing the profile you get when you have the spectroscopic sample with brown and the photometric one with red. As you can see here in the top, the signal to noise of these two measurements is comparable. However, the spectroscopic sample has a fourth, more or less, of galaxies compared to the photometric sample. And as we can see here, we find consistency between the two profiles. These differences are mainly due to noise, and as I mentioned before, the larger scales are subject to noise coming from the CMB primary anisotropies. And these are highly correlated, and therefore that's why you can see a difference on large scales. Finally, we included a signal to noise ratio forecast of what would be the signal we expect with future surveys. And as shown in here, we expect that DESI year 3, which is the next data set from DESI, we expect to have a signal to noise approximately of 20. And when we studied the simulated counterpart of LSST through the red magic sample, we find that their signal to noise could be as high as 50, which of course gives us a lot of hope to study the gas at different redshift, stellar masses, and other components. As a conclusion, I just want to say that this study allows us to measure the highest signal to noise kSZ measurement through the stacking method we have ever done. With this, we have found that gas is definitely more extended than dark matter, and also hints of a large baryonic feedback on the observed sample. We also did study redshift mass luminosity dependence, which hints us a lot about galaxy formation models. We also observed the kSZ profiles from other types of galaxies, such as the BGS and the ELG samples. And we found coherence with photometric kSZ results, which is great news for example, Rubin Observatory, which is starting pretty soon, and we expect to have way more galaxies. I hope you enjoyed this talk and hope to see you during the discussions of Cosmology from Home.